There was a time, long before Earth, long before stars, long before light, when the universe was dark. No galaxies, no suns, no planets, no color, just a vast, expanding silence. Then something changed. Hydrogen stirred, gravity pulled, and suddenly the first stars ignited, blazing into existence, tearing through the darkness with light that had never shone before. This was the cosmic dawn, the moment the universe awoke. And for the first time in history, we now have a telescope capable of seeing it. The James Webb Space Telescope, JWST, is humanity's most powerful window into the past. A machine built not just to observe the universe, but to rewind it, to capture the light of the very first galaxies, those that formed just a few 100 million years after the Big Bang. What were those galaxies like? How did they form? And what do they tell us about our own beginnings? This is the story of how we are witnessing the birth of the cosmos itself, not in theory, but in light. Light is more than illumination, it's memory. The farther we look into space, the further back in time we see, because light takes time to travel. When we observe the moon, we see it as it was 1.3 seconds ago. The sun, 8 minutes ago. Alpha Centauri, for years. But with powerful telescopes, we can go much, much further. The Hubble Space Telescope, launched in 1990, gave us our first deep glimpses into the early universe. Its ultra-deep field revealed galaxies billions of light years away, tiny smudges of light, ancient and delicate. But Hubble had a limit. It could only see so far. Enter JWST, a telescope 100 times more powerful, optimized not for visible light, but infrared. Because as the universe expands, light from distant galaxies is stretched, redshifted, beyond the visible spectrum. What began as ultraviolet or visible light becomes infrared by the time it reaches us. To see the earliest galaxies, you need to see in infrared. That's exactly what JWST was built to do. JWST is not just a bigger telescope. It's a cosmic time machine. Launched on Christmas Day 2021, JWST now orbits 1 million miles from Earth at a gravitational sweet spot called Lagrange Point 2. It carries a massive 6.5-meter gold-coated mirror, folded like origami during launch and unfurled in space with surgical precision. It's shielded by a multi-layered sunshade the size of a tennis court, keeping its instruments cold, just a few degrees above absolute zero. Because to detect faint infrared light from ancient galaxies, any heat at all is noise. JWST was designed for one purpose: to see what no telescope has ever seen, the first light in the universe. And it has already delivered. Within weeks of becoming operational, JWST began surprising astronomers. Its early images, deep field surveys of seemingly empty space, revealed hundreds of distant galaxies never seen before. Some of them were shockingly old. Others were shockingly bright. One of the first to catch attention was a candidate galaxy dubbed Glass, Z13, possibly formed just 300 million years after the Big Bang. Then came others: Source 93316, Jades, GS, Z13-0, and more, each potentially rewriting our timeline of when galaxies began. They appeared earlier, more massive, and more organized than expected. That was the surprise. According to existing models, galaxies shouldn't have formed this quickly or become this bright, this fast. But JWST was showing us that the early universe may have matured rapidly, forming stars and structures with astonishing speed. In short, the universe's baby pictures looked far more developed than we thought. To understand why this is so profound, we have to imagine the conditions of the early universe. After the Big Bang, roughly 13.8 billion years ago, the universe was hot, dense, and filled with a plasma of particles. Light couldn't travel freely. But after about 380,000 years, the universe cooled enough for atoms to form. The cosmos became transparent, and the first light, the cosmic microwave background, was released. Even then, there were no stars, just dark clouds of hydrogen. It took hundreds of millions of years for gravity to pull that gas into dense knots, collapsing into the first stars. These first stars, called population 3 stars, were likely massive, dozens or hundreds of times more massive than our sun, and burned hot, fast, and bright. They lived short lives, exploded as supernovae, and seeded the universe with heavier elements, laying the foundation for the first galaxies. JWST is now catching the light of those first structures, galaxies so ancient that their light has been traveling for over 13 billion years. We are seeing them not as they are today, but as they were at the very beginning. The galaxies JWST sees are not just beautiful, they are clues. Their shapes, their sizes, their brightness, their spectra, all of it tells us how the universe evolved and how it gave rise to the galaxies we see now. Galaxies like the Milky Way didn't just appear. They grew from smaller proto-galaxies, merging, interacting, and transforming over billions of years. By studying early galaxies, we can learn, when the first stars formed, how fast galaxies built up mass, when elements like carbon and oxygen appeared, how supermassive black holes formed so early. Yes, JWST has also found evidence of black holes in early galaxies, possibly just 400 to 500 million years after the Big Bang. How did such massive black holes grow so fast? No one knows. But JWST is giving us the data we need to find out. It's not just looking back in time. It's helping us reconstruct the family tree of galaxies, the origin story of everything we see, including us. Every image from JWST is a surprise. Galaxies with strange spiral arms, massive star clusters, unusual colors, peculiar spectra. Some galaxies appear to defy current cosmological models. They shouldn't be there. Not that big. Not that soon. This has sparked intense debate. Do we need to revise our models of star formation? Have we misunderstood how quickly galaxies can grow? Is something wrong with our understanding of dark matter or dark energy? JWST isn't just confirming theories. It's challenging them. That's what science is supposed to do. And JWST is doing it faster than anyone expected. Cosmic Dawn is just one part of JWST's mission. It's also peering into the atmospheres of exoplanets, studying the life cycles of stars, revealing star-forming nurseries, and mapping distant quasars. But its glimpse into the first billion years of the universe may be its most transformative legacy. We are watching the universe wake up, seeing the first sparks of structure, complexity, and light. In the coming years, JWST will push even deeper. With longer observations, better calibration, and more advanced data processing, we may soon detect the very first generation of stars, the true population 3 stars never seen before. And with them, we'll witness the moment the universe lit up, the moment it became what we know today. We often ask, where do we come from? JWST is helping us answer that, not with philosophy, but with photons. Ancient light, stretched by time, arriving at our eyes after billions of years in flight. That light carries a story, not just of galaxies and stars, but of the origins of structure, of chemistry, of life. Because everything we are, every atom in our bodies, was forged in the hearts of those early stars. Their explosions seeded the cosmos. Their gravity shaped space. Their light now falls on our detectors. And as we collect it, pixel by pixel, we're not just seeing into the past. We're seeing ourselves.